Okay, so today we're going to kind of pick back up with exponential and logarithmic equations. We're going to do some kind of real world applications with those today. So just a couple of quick examples and I'll let you get going on your assignment for the most of today. So today we're going to talk about tripling time, doubling time, tripling time, and half-life. All right, so typically with doubling and tripling time, we use continuously compounding, right? So our continuously compounding formula, all right, was A is equal to P e to the RT, all right? So let's just talk about doubling time, all right? Now, obviously doubling time is the amount of time that it takes some investment to double, all right? Remember, P here is my principal or initial amount, all right? So we can pick any number that we want here. It doesn't matter, right? Let's just pick 100, all right? And then we'll still have this e to the RT. Well, if we start with 100, what is double 100? 200, all right? So that's what we would put here, all right? Now it asks for doubling time, so obviously we're going to want to solve for t here, okay? So first I need to get rid of this 100 over here, all right? And then of course this just simplifies to 2, which is always going to be the case no matter what number you pick here for p, and then of course if you double it, right, whenever you will divide, you'll always end up getting 2 here. So now we have 2 equals e to the RT. All right, well, this is in exponential form, all right? So remember, we have our definition of logarithm that says if we have log base b of a is equal to c, if and only if b to the c is equal to a. All right, so this obviously looks like this. All right, so I can rewrite this, all right, as log base e of 2. Remember, log base e is just ln. And then this will be RT. All right, well, if I'm trying to solve for t here, all I have to do is divide both sides by r, all right, and I'm done. So t is equal to ln of 2 divided by r, right? So if you're talking about compounding continuously, all right, this is all we need, right? You don't actually have to go through this whole process every time, unless, of course, you don't remember the formula. Then, of course, you always can. You'll get to the same place, all right? But as long as you know the interest rate, right, all you have to do is ln of 2 divided by the interest rate, and that will tell you how long it takes to double, all right? Tripling is going to be very similar. What do we think the only difference is between tripling? Right, so what number is going to change? Yeah, the 2 is going to become a what? 3. All right, so for triple time, right, we just have ln of 3 over r. All right, and then of course our half-life, all right, I wrote this on the board before. Our formula for half-life is A is equal to P times 1/2 to the T over K power. All right. So that's the half-life formula? Yep, this is half-life, absolutely. All right, where of course P is still our principal or starting amount, A is still our final amount, T is still time in years, all right, but K is the half-life of the element. All right, now do be careful, all right, because half-life and time will both be given in years. So a lot of people will inadvertently flip those around. All right, now on Delta Math, I do believe that they will also talk about doubling and tripling time with compounding in other ways. Okay, that's not a big deal. All right, remember that our formula for just regular compound interest is A is equal to P times the quantity 1 plus R over N, all to the NT power. So again, of course, they would tell you how, whether it's compounded annually, monthly, quarterly, whatever, which is what you would plug in for both of these n's.
So that's a compounded equation?
Yeah, this is just regular compound interest here. And up here, the PERT is compounded continuously. And these three formulas we went over last week. All right, so if they say some, it's being compounded some way other than continuously, you're going to use this. Of course, doubling time, you can still just pick any number you want here and double it. Tripling time, you pick any number you want here and triple it. You can even pick one, right? Like you don't have to pick 100 or whatever, like I did over here. It's all going to work out the same anyway. Right, so do keep that in mind. Okay. So you have deposited $500 in an account that pays 6.75% interest compounded continuously. How long will it take for your money to double? All right. Well, we just kind of figured out on that last slide that doubling time for compounded continuously is T is equal to ln of 2 over R. Right? Remember, this initial amount doesn't really even matter. Okay. Because if you double it, you're going to take 1,000, and then when you divide both sides by 500, you're just going to get that 2, which is where this 2 pops up from in this formula. All right, so all we really have to do is say T is equal to ln of 2 divided by the interest rate. Remember, we do have to write that as a decimal, so 0.0675. We can just come to our calculator here, and we can say ln of 2 divided by 0.0675. Bam. All right, so this will be 10.269. And of course, that is in years. So that's it. Double time, especially with compounding continuously, is very straightforward and simple. Now, like I said, if you don't remember this formula, it's not a big deal, right? You could still always say A is equal to PE to the RT, right? This is 500. R we know is 0.0675. This would have to be 1,000 if we're doubling it, right? You divide both sides by 500 here. So you get 2 is equal to E to the 0.0675 t. All right. You could use your definition of logarithm to rewrite this exponentially, and you would get ln of 2 is equal to 0.0675 t, and then you would divide by 0.0675.
So,
yes. Right. So if you kind of remember this formula that we kind of derived, right? We kind of got here and said, okay, well, now when we're talking about doubling and tripling time, we don't have to do all of that work again. We can just always jump straight to here, all right? So it just makes life a little bit easier. All right, go ahead and try this one. All right, but now it talks about tripling your money.
Is this all we have today?
Yeah, pretty much.
So then pretty much today we just do Delta Math.
Yes. And there'll be like all of your delta math today will be, doubling and tripling time, half-life, and other compound interest problems, which we'll do some examples here shortly.
The other day, I tried to get on the calculator at my house and it didn't work.
Yeah, some students have had that problem in the past. I would take your tablet to the help desk whenever you have time and tell them, and I think there's something that they can do. For some reason, some students works perfectly fine at home, and other students, when they go home, it just doesn't work. I have no idea what that's about, but
We just use the calculator 85 out.
yeah, absolutely.
Is that on our phone?
Yeah, you can download it. It's free. It's called Calculate 84. Some things don't work quite as well. Um, Specifically, like the second trace feature, where you find like zeros, intersections, and that kind of stuff. It's a little off for some reason. Um, so if you're ever finding zeros or intersections, I would probably recommend Desmos. Just go to desmos.com. Because that'll be a little bit more exact. For some reason, it's a little weird on there. I don't know why. Okay. Anyway, let's go ahead and take a look at this, though. Of course, we can use our formula T is equal to, yep. Oops.
They have a chart feature on the calculate 85, but it doesn't work. There's no way to get to it.
Yeah, the table feature. Yeah, it's really weird. Like, there's a couple of weird things about, for 98% of the stuff, it works just fine, especially when you're just like trying to use it as a regular calculator with all your exponentials, ln's, all that kind of stuff. But there's a couple of weird things on there that just don't work very well. All right, so here we've got ln of 3 divided by our interest rate of 0.028. All right, so again, we use our calculator here. We say ln of 3 divided by 0.028, 39.236. And that is years. Good times. Okay. So, from 1985 through 2007, this should be the average salary, Y, in thousands of dollars for public school teachers for the year T can be modeled by the equation Y is equal to negative 2.983 plus 15.206 ln of T. All right, and this is good for T between 5 and 2007. I'm sorry, between 5 and 27, where T is equal to 5 represents 1985. All right, and of course, 27 would represent 2007. All right, during which year did the average salary for public school teachers reach $45,000? Okay, so let's all right, so we need to get this copied. And we want
whatever formula they give us, we have to use it.
Yeah, I mean 99.9% of the time, yeah. All right, so here's the formula that they give us. All right, and we're wanting to find when the average salary is $45,000. Now we do have to be careful here, all right, because it says that Y is in thousands of dollars, okay? So you don't actually make Y 45,000, you make Y simply 45 because it says that it's in thousands of dollars, okay? Okay, so we're trying to solve for T here, all right? So first thing I'm gonna do is add 2.983 to both sides. So we're going to get 47.983 is equal to 15.206 ln T. Yep. So we divide both sides by 15.206. All right, and I'm just going to call this stuff, so I don't have to rewrite it every time. That's just my stuff. All right, well now this is in logarithmic form, so I can use that definition of logarithm. Remember, ln is just log base e, so this is e to the stuff power is equal to t. All right, so if I think of it that way, all right, I can say e raised to the, all right, and up top I have 47.983. Down below I have 15.206. All right, so 23.465. All right, so it says that 5 is equal to 1985 and 27 is equal to 2007. So what would 23.465 equal? All right, that would be like 2003, somewhere in there, right? However, they do weird things, and I don't like the way that they do this, but I know they do it in college, and I think they do it on like the SAT and stuff too. So whenever you're talking about time like this, no matter what this is, you round up. So you would actually say 2004.
Wait, how do we know some of that? Like, how do we know 2004?
Because it says up here, right? It says here that when t is equal to 5, that represents 1985. So 6 would be 86, 7 would be 87, dot, 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 right? So 27 is 2007. Does that make sense?
Yeah.
So if 27 is 2007, then 23 is 2003, but because it's somewhat after 2003, right? Like any amount of time after 2003, we say 2004. Does that make sense?
Yes, sir.
Okay. All right. All right, the number of y, all right, this is the exact same thing, basically, the exact same, type of problem. So why don't you guys go ahead and try it out? It'll work exactly like that last one. And then again, we have this, where t represents the year and t equals 6 is 1996, right? Which means t equals 19 would be 2009. All right. So go ahead and work out this problem just like we did the last one and try to get that in which year this would occur.
So what number would we put out in the front?
In the front, it says when the animal species reached 923. So you would put 923 because it doesn't say that it's measured in thousands or that it's measured in whatever. So if it doesn't specifically state that, then whatever the number is what it is. Yep. Yeah, sometimes the wording, you kind of have to be careful, like in that last problem where it told us that y was in thousands. But in this case, it is not.
Where's E on the calculator?
E, you can, like if you want E raised to some power, you can hit second ln.
Okay.
Yep. Okay, so we can definitely right, so if we just go ahead and plug in our 923 in for y here, because they wanted to know when the number of endangered species would reach that number. All right, so first I'm going to subtract 702 from both sides. So that'll leave me with 221 here. And then, of course, we divide by 79. All right. And then here, again, ln is just log base e. So we can rewrite this in exponential form. So e to the 221 over 79 power is equal to t. All right, so t is equal to, if we use our calculator here, then we should get 16.403. All right.
207.
Yep, that sounds about right. Yep. right? Because it's a little bit past 2006, so 2007. All right. Good times. Of course, we don't need to worry about that. There's a couple more things I want to show you. Not much at all. Basically, I want to get to this example, and then I'll let you go. All right. So here we've done compounding interest. Here. All right, we've done compounding interest before, where we were finding the future rate or the future value. All right. Well, I kind of want to talk about how we find other things as well. Okay. So here, doubling time we've already talked about, but we also kind of want to talk about, what if we have to find the interest rate or the initial deposit, or we can find other things other than just the final value or the doubling time. Okay. So here, doubling time is going to be pretty easy, right? We know that doubling time, or not. All right. We know that doubling time is equal to ln of 2 divided by the rate, which in this point is 0.086. All right, so we use that on our calculator. And you get 8.060 when rounded. All right, and then the amount in 10 years. So here we would use, we're using compounded continuously here, right, which is what it tells us up here. All of them. All right, for this whole table. All right, so we know that A is equal to P, which is my initial amount, which in this case is 1,000. Whoops, not 100, 1,000. Times E to the RT, so 0.086, and T, of course, here is 10. All right, so all I have to do is plug that into our calculator. So 1,000 times E raised to the 0.086 times my T, which is 10, 2363.16. All right, so we are good there. All right. All right, so now let's try this next one here. All right, we know again we're given some doubling time stuff here. All right, and here's the initial deposit. All right, and now I'm looking for the rate. Okay, well, actually, if you kind of think of it generically, right, as far as A equals PE to the RT. All right, well, now we're trying to find the rate instead of the doubling time, but we're still doubling, right? So this is still 2 to this 1, and then we still have the exact same thing here. So 2 equals E to the RT, which means ln of 2 is equal to RT. Well, this time I'm trying to solve for the rate, so I actually want to divide by T, right? So it's really the exact same thing, except now I'm dividing by the time to get the interest rate. Does that make sense? All right, so in this case, my interest rate is going to be ln of 2 divided by my doubling time, which is 15. So we can do that here, ln of 2 divided by the doubling time, which is 15, to get my interest rate of 0.0462.
So 4.6%.
Yep, 4.62%, absolutely. All right, and then of course, again, the amount in 10 years. All right, we still just use our A equals PE to the RT. All right, so A equals PE to the RT. All right, so now we've got kind of everything that we want here. A is equal to P, my initial deposit is 2,000, times E to the 0.0462 times 10. So we've got 2,000 times E to the 0.0462 times 10. And 3174.49. 3174.39. All right, so, just be mindful that we're not always solving for the final amount, or we're not, we can solve for anything. We can solve for the final amount, we can solve for the initial amount, we can solve for the time, we can solve for the rate. If it's not continuously compounding, we could solve for the number of times compounded per year. Right? We can solve for any variable, um, assuming that we're given every other piece, right? As long as there's only one missing variable, we can solve for it. All right. So that's really going to be it for the day. All of your delta math stuff will be based off of this stuff. Half-life. Um, let's see, is there a half-life problem here? No. Okay. So half-life, compounding interest, that kind of stuff. All right. Okay. If you have any questions, just let me know.